You ever wonder how an AI looks at our messy, chaotic world and makes any sense of it at all? I mean, when it sees a picture, how does it figure out what's the actual object and what's just its shadow? How does it find the signal in all that noise? Well, that's the fundamental mystery we're going to try and untangle today. So this quote from the paper we're looking at, it really gets to the heart of the matter. It's saying that an AI is basically only as good as the data it's given, or more specifically, how that data is represented. For a long time, we humans had to do all the heavy lifting. We do this thing called feature engineering, where we literally tell the machine, hey, pay attention to these pixels, but ignore those ones. And as you can probably guess, that was incredibly slow and it put a serious limit on what AI could actually do. And that right there, that's the big question that drives this entire field. What if we could stop holding its hand? What if the AI could become its own detective and figure out completely on its own what features really matter and how they all fit together? This is the whole quest of representation learning.
Okay, so how does a machine even start to tackle a puzzle like this? Well, it turns out there are two main schools of thought, two big approaches to learning a good representation from all this raw, messy data.
This slide lays out two really different ways of thinking about it. On one side, you've got learning invariant features. The goal here is pretty simple. Just learn to ignore the stuff that doesn't matter. Toss out the noise. But on the other side, you have disentangling explanatory factors, which honestly is way more ambitious. The goal isn't to just throw information away, but to carefully pull apart and organize all the different things that are causing the data to look the way it does.
Let's make this super concrete. Imagine an AI sees a picture of a ball and its shadow. The invariant approach says, okay, to know it's a ball, just ignore the shadow completely. Simple enough. But what if the direction of that shadow could tell you where the sun is in the sky? Well, too bad. That information is gone forever. The disentangling approach is so much smarter. It learns two separate things. One, the actual shape of the ball, and two, the properties of the shadow. All the information is still there, it's just been neatly sorted into different boxes. And that's exactly why disentangling is so powerful. It's all about building a really robust and flexible understanding of the world. By separating all these factors, instead of just throwing them in the trash, the AI doesn't have to guess what might be important for some other task down the road. It keeps all of its options open. And this slide, this is really the core definition from the paper. A good representation isn't just a summary. It's an organized, disentangled map of all the hidden causes that created the data in the first place. That's the real endgame.
All right, so we know what we want, this beautiful, disentangled representation. But how in the world do you get a machine to actually do it? Well, the tool that makes all this possible is something called a deep architecture.
Honestly, the best way to think about it is like building with Legos. A deep learning model doesn't try to understand a whole complicated picture all at once. No way. Instead, it builds its understanding layer by layer, creating this hierarchy where simple little pieces get combined into bigger, more complex ones. So let's see how this actually works. At the very first layer, starting with nothing but raw pixels, the network just learns to see the most basic building blocks of our world. We're talking simple edges, corners, little gradients of color. Think of these as the tiny one-by-one Lego bricks. Okay, so the next layer up takes those little bricks, the edges and corners, and it starts snapping them together. It learns to recognize slightly more complex things, like a rough texture or a simple circle. It's starting to assemble the basic bricks into something more meaningful. And as you keep going up layer by layer, these constructions get more and more abstract. The model combines textures and shapes to recognize parts of an object, like an eye, or a nose, or a car's wheel. And then at the very top, it puts all those parts together into the final concept, like face or car. This whole hierarchical thing, where the same basic features can be reused over and over to build tons of different complex objects, is what makes deep learning so incredibly powerful. Now, to really get why this deep, layered approach was such a huge deal, it helps to look at what came before, these older, sort of flatter methods.
And the difference is just stark. For decades, one of the go-to approaches was using linear models like principal component analysis, or PCA. Now, PCA is great at finding the single biggest source of variation in your data. But deep architectures build that rich hierarchy using stacked, nonlinear operations. And that nonlinearity, that's the secret sauce. Here's why. If you stack a bunch of simple linear operations on top of each other, all you get is another simple linear operation. You can't build real complexity. It's like trying to build a giant, intricate Lego castle using only one type of flat brick. It just doesn't work. Nonlinearity lets each layer twist and warp the data in a totally new, more complex way.
This all sounds great, right? But it brings us to one of the biggest, toughest challenges in this whole field. It's one thing to want the AI to disentangle all these hidden factors, but it's another thing entirely to actually tell it how to do that. So here's the real problem. In a normal machine learning task, like classifying images, the goal is super clear. Is this a cat or a dog? You have a right answer. But with representation learning, the objective is, well, it's fuzzy. We're telling the machine to go find the interesting independent causes of the data, but we don't know what those causes are to begin with. It's like telling a detective, hey, go solve the crime, but not telling them what the crime even is. And because this is so hard, researchers often use these little shortcuts called priors, which are basically just built-in assumptions about the world. For example, a temporal coherence prior just assumes that things happening close together in a video are probably related. Or a spatial coherence prior assumes nearby pixels probably belong to the same object. Now, these are really useful hints, for sure, but they are not the same as the real goal of factor disentangling. It's the difference between making a good guess and having a genuine understanding.
So why? Why do researchers pour so much time and energy into solving what seems like an impossibly hard problem? Well, because getting this right is absolutely fundamental to the entire quest of building true artificial intelligence.
The ultimate payoff is this: an AI that learns a truly disentangled representation of the world hasn't just learned how to do one little thing. It has learned a flexible, robust model of reality itself. It can then take that one single representation and use it to solve all sorts of different and even totally new tasks in the future. I mean, think about what that means. A self-driving car that understands the difference between a real person and their shadow on a foggy day. Or a medical AI that can separate the tiny signal of a disease from the noise of a blurry scan. It's about building AIs that can actually generalize, and that's a huge step towards real intelligence.
Which, of course, leaves us with one last really fascinating question to think about. If a machine can look at the world and not just see surface-level patterns, but can actually separate the fundamental underlying factors that cause those patterns, the object from its shadow, the speaker from their voice, has it moved past just calculating things and actually started, in some real way, to truly understand?